All right, let's start Unit 2 here. Unit 2 has to do with matter. We're going to start actual chemistry stuff instead of general science and math questions. And 2.1 is I can define matter and each phase of matter based on shape, volume, and particles. So this might be a review a little bit from middle school. This is basically the difference between solids, liquids, and gases. Chemistry specifically is the study of matter and how it changes. And matter is anything that has mass and occupies space. So things that aren't matter basically is just the various forms of energy. Okay, so the difference between solids, liquids, and gases can be defined of the shape that they hold, the volume that they occupy, how the particles are moving, and then we're going to draw a diagram that hopefully represents all of that. So the shape of a solid is it holds its own shape. And a different way of saying that is that it has a defined shape. So an ice cube, you can mold it into any shape that you want and it will hold that shape. That shape is not going to change by itself. Liquid takes the shape of its container. So if you have liquid water, it's going to take the shape of whatever you put it in. Another way of saying that is it has an undefined shape. So if it has an undefined shape, it just depends on the container. If you put it in a triangle container, it's going to be the shape of a triangle. If you put it in one of those fun cups that have weird shapes, it's going to be a fun, weird shape. And then gases are also undefined. They take the shape of whatever bottle they're in. And if you open the bottle, the gas is going to rush out of that bottle and take the shape of the room. Solids have defined volumes. That means it's measurable. You can measure it and determine it. It's not based on anything else. Liquids are also defined. Usually you have to pour them into a graduated cylinder, but you can determine its liquid or its volume. And then gases are undefined. So gases' volume will change based on whatever container you have it in. So if you have a soda pop, that's probably about a 20-ounce bottle or something. The gas is in there. And then when you open it, that gas rushes out into the room, and now that gas occupies the volume of the whole room. So it depends on what container it's in for the volume of the gas. Solid particles are fixed in place. They don't move around. They are moving, but they just kind of vibrate. Gotta make sure I spell that right. So they're fixed in place, they're not moving around, and they're just kind of wiggling. Liquids are mobile, which means they can move around, and they move slowly. So now they're doing a little bit more than vibrating, they're moving around slowly. Gases are also mobile. These move quickly and are far apart. So solids and liquids are about the same size. If you melt an ice cube, it's really not that much smaller or bigger than before. But gases, you can boil water into steam, and that steam can take up a lot of space, or a little bit of space, depending on how pressurized it is. So for the drawing of the diagrams, I'm going to pretend this is a box. So if I put an ice cube in the box, it might look something like this. I'm going to try to draw 15 circles there. So there's my ice cube in the bottom of the middle of the box. When that ice cube melts, it is going to take up all of the bottom of the box. 8, 9, 10, 11, 12, 13, 14. Where's the 15th one going to go? There. Okay. So gravity is going to pull all of the particles down. And since they can move, since they're mobile, they're not just going to stay like this. They're going to spread out to the bottom of the box. Then when it's a gas, now they're going to be moving quickly and far apart. So now I'm going to space them far apart. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There, now they're spaced far apart in that box. And as you can see, the volume expands to fill up the entire container. Okay, there are different properties of matter. There's physical and chemical. Physical properties, basically you can just look at and observe. You don't actually have to do any experimenting or changing of the substance. If you're determining a physical property, you're not changing what it is. So examples are color. I can write down the color of something without changing what it is. Density. I can measure the density of something without changing what it is. Temperature, I can take the temperature of something without changing what it is. Length, etc. Mass. I'm just going to do dot, dot, dot. It's anything that you can measure or determine without actually changing what chemical it is. We'll get into chemical properties later, and that'll make more sense. Okay, then there's extensive properties. So extensive properties depend on how much you have. So here's 3 examples. I don't have to write any. Mass, volume, and length. If I have more of something, it's going to have more mass. If I have more of something, it's going to take up more space. If I have more of something, it's going to be longer. So those are extensive. Intensive properties don't change based on how much you have. So temperature. If I have more or less of air in this room, that doesn't change the temperature of the air in this room. If I have more or less of a whiteboard, its color does not change. It is still a whiteboard. Hardness. If I have more or less of a rock, it doesn't change how hard it is. Melting point. If I have more or less water, it doesn't change the fact that it always melts at 32 degrees Fahrenheit. Boiling point, again, doesn't change. Pressure won't change. Molecular weight, don't know what that is yet. You'll figure it out later. And then density is the one people goof up all the time. If I have more of something, it will weigh more, but its density will be the same, because density is based on mass and volume, and both of those scale proportionally. So when you do the division of mass divided by volume, it should equal out, and it won't actually change. Okay, now we go to chemical properties, and these are the ability of a substance to combine with or change into one or more other substances. So these properties tell how something is going to change. I should go back and give you a few examples. So chemical properties, you have to change the substance in order to determine if it's a chemical property. The easiest one to explain is flammability. So in order to figure out if you can burn something, you need to burn it. When you do burn something, it changes what it is. For example, if I burnt paper, I would no longer have paper. I would have smoke, ash, carbon dioxide, water, etc. Everything that the paper would turn into, I would have. But the only way to figure out if it's flammable is to set it on fire first. The other thing is whenever it says reacts with. So there's a million different chemicals, so you could list a million different things here. But in order to determine if it reacts with something, we need to react it with that thing, and then we'll make a new, different chemical. Common ones that you'll see are acids, water, air, and oxygen, O2. So a lot of times it'll say it's highly reactive with air or highly reactive with acid. Very corrosive is another word. Corrosive is if it dissolves other compounds easily, and compounds that aren't already dissolvable in water. So these would be acids themselves. Great. Okay, guided practice. Identify the following as being intensive, extensive, or chemical. So we have mass. You can determine mass without changing it. So that is a physical property. The mass will change if you have more of it. So this is extensive, physical. The boiling point of ethyl alcohol is 77. Boiling point won't change based on how much you have. So that's extensive. And then the fact that it's boiling point, we don't have to change it to boil it. You're just changing its phase. So it's physical. Oops, I screwed that up. Boiling point, if you have more or less of it, it's intensive. Because if I have more ethyl alcohol, it's not going to boil at a different temperature. Whether I have a little or a lot of ethyl alcohol, it's going to boil at 77 degrees, but it still is physical. I got that part right the first time. 3, baking soda reacts with. Oh good, that's chemical. And then, since it's chemical, is it extensive or intensive? Well, if I have more of it or less of it, it's still going to react with vinegar. So this is still going to be intensive. It doesn't matter how much I have, it's all going to react with vinegar. 4, the density of mercury. So density is physical because I don't have to change it. And then it's not going to change if I have more or less mercury. So it's intensive. 5, solubility. That's whether it dissolves or not. If I have more of it or less of it, it doesn't matter whether it dissolves at all or not. If I have a little bit of salt or a lot of salt, it's still going to dissolve. So that's intensive. Since it's solubility, I'm putting, let's say, salt into water. Before I do this process, I have salt and water. After I mix them together and stir it around, I still have salt and water. They're just combined. So this is a physical property. There's only one chemical in there. Physical versus chemical changes. So this is similar to physical and chemical properties. A little bit different though, because you have to do a chemical change to determine a chemical property. So physical changes is a change that happens that doesn't change what it is. It's still the same chemical. Take, for example, this paper. If I rip it in half, it's still paper. So this is a physical change. In middle school, it's commonly taught that one is reversible and one is irreversible. That is not actually what it is. That's just a helpful guideline that will sometimes get you the right answer. This is a physical process that is irreversible. There's no way to get this paper exactly the same way it was. Of course, I can tape it together, but now I've added a different few chemicals to it. So the chemical that it is not going to be the same that it was before. Phase changes are the ones that trip people up the most, because a lot of times we think of water and ice as different. They're actually the same thing, just two different phases of the same thing. Chemical changes, we're changing what chemical it is. Decomposing is a great example. So if you have a log that is decomposing, it's going to get broken down into smaller and smaller particles, and by the end of the day, you're just going to have a bunch of dirt. And I think you know the difference between a log and dirt. Think. Another good example is molding or rotting food in the fridge, because it's going to change color. So a red strawberry will get green mold on it, or the smell or taste will change if you think of food going bad. These are general guidelines to tell if a chemical reaction has happened. Color change, so this is the strawberry changing from red to the moldy green. Bubbling, fizzing, or gas formation. So when you react baking soda and vinegar, you get the volcano effect, and you're going to get a lot of bubbles. And the formation of a solid. This one's a little trickier, and you don't really see this one in everyday life. But if you mix two liquids together, sometimes you'll get a solid come out of it, and that is a chemical reaction. There are exceptions to this. You can change color without it being a chemical reaction. If you put food dye into water, it'll change the water that color, but the water's not actually changing the color, because believe it or not, water is colorless. It is completely devoid of all colors. So all you're seeing when you put the green food coloring is you're seeing the green food coloring spread out. So you're not actually making a new chemical. It's the same chemicals, they're just getting mixed together. Bubbling, fizzing, and gas formation, that is not a chemical reaction when you're boiling water. You are making bubbles, but those bubbles are just the gaseous phase of water, which you already have. Then the formation of a solid, what is not a chemical reaction, is like snow or hail, because again, it's just water solidifying. Okay, the change of matter, burning toast. So there's a little bit of color change there, especially if you leave it in too long, it'll get nice and black and crispy, and it tastes different. So this is a chemical change. Making ice cubes. Before you make the ice cubes, you've got water. After you make the ice cubes, you've got water. So it's a physical change. Lighting a candle. Before you light the candle, you have candle wax. After you light the candle, you have melted candle wax, but you've also generated a little bit of smoke and water. So the only thing that's happening is not the melting. There's also some of that candle wax being turned into carbon dioxide and smoke. So this is mostly chemical. I guess you could consider it both if you're also thinking about the melting of the wax. Spoiling milk. So here we've made a solid, and it tastes and smells different. So that's chemical. And then making of Kool-Aid, that's going to be physical. Because if you taste the Kool-Aid before and after, it's the same taste. Obviously, if you're just eating the powder with a spoon, it's going to taste stronger than the liquid version, but it shouldn't taste different. That's it. We are done with 2.1 through 2.3. So in the next video, we'll start at 2.4.